Chapter 9, we're going to be taking the quadratic expressions that we're working with from Chapter 8, and we're going to be putting them into equations now. So 9.1, we're going to be looking at those in terms of graphs, quadratic graphs, and their properties, so basically their shape. So I'm going to skip over most of that first question, but it is showing up the type of equation we're going to be using here. Again, we're using quadratic expressions, kind of like with last time. But in this case, we should be able to put those into, again, an equation and use that to eventually come up with solutions. That's going to be most of our work in Chapter 9. Again, we call those quadratic functions. That's nonlinear, and it models situations where change is not constant in real life. So our classic situation, something's falling, it's acting on gravity, it's falling faster and faster. So that quadratic function is going to look a lot like our quadratic expressions from before, ax squared plus bx plus c. Now we're just throwing y equals in front, so we're making that an equation. And if we can make it an equation, we can find solutions and we can graph it just like our linear equations. So the simplest quadratic function, just like our parent functions with our linears, we can use that as a parent function for a quadratic. So now instead of just y equals x, we got y equals x squared. What that graph is going to make is a U-shaped curve that we call a parabola, and that's our parent function, y equals x squared. Again, that's our simplest U-shape that we can make. I also have symmetry. I noticed that the right-hand side is the exact same as the left-hand side. If I imagine this line going through the center, and that line that going through the center, we're going to call that the axis of symmetry. A lot of cases also, I'm just going to abbreviate that as AOS. So if you ever see AOS, I'm just using that to mean our symmetry going through the middle of our parabola. So we also have the highest and lowest points on a parabola. That's going to be important. We're going to call that our vertex. And again, it's going to lie on the axis. So it's going to lie basically directly through the center. So what we're going to see is two basic shapes. If our first term is positive in that equation, ax squared plus bx plus c, means that parabola is going to be opening upwards. So a basic example of that, let's say if I do something like y equals 2x squared, I know just by looking at the equation, positive 2 means it's going to be opening upwards. And let's say if I reverse that, so if our first term is negative, and I could just say y equals negative 2x squared, just by looking at that negative equation, I know in this case parabola is going to be opening downwards just by starting with that negative. So let's examine the first case. If I have an upwards opening parabola, 2x squared, that means if it's opening upwards, and actually, let me examine that example from below. So this is our vertex. Our graph opening upwards would have a positive equation, and that means that our lowest point is going to be at the bottom of this U-shape. So our lowest point is going to be what we call the minimum point. If I have a graph that's opening downwards instead, again, that would be if I had a negative equation. A downwards opening parabola is instead going to have a maximum point, and that would still be what we call a vertex. So if all I'm asked to do is to find the vertex, I just got to find out where's our highest or our lowest point. So in the first example, looks like our highest point's right there. So all we got to do is say that the vertex in this case, if we can identify the coordinate, looks like it's just at 0, 3. So you can say the vertex is at 0, 3. And I know that since it's at the top of that U-shape, we can just call that a maximum point instead of a minimum point. All we got to do is pick out the top of the curve and identify that it is the top rather than the bottom. So next example, we see that the vertex is at negative 2, negative 3. And instead of being a maximum, now since it's at the bottom of this U-shape, we just call that vertex a minimum point. And if I was to graph the whole thing, in this case, we just had to point out where the top or the bottom was. But if I did want to graph the whole thing, I could start from that vertex and then start graphing one side. Because if I use the fact that we have symmetry, I can reflect that side and then create the U-shape using our axis of symmetry. So for example, I could start from the vertex, find a point on one side of the parabola, and then if I reflect that point over the same distance on the other side from my axis of symmetry, that's going to create the other half of my parabola. Graph one half using our points, graph the other half using reflection. And for our cases, we're always going to be using the vertex at the origin to start with, and that means the axis of symmetry is going to run through your y-axis. So if you're starting to graph these, we can graph these just like how we started graphing our linear equations. I can take our table of values that we have, what I started to make off to the left here, plug some x's in, and just see where my y's are going. So if I took 0, plug that into the quadratic function 1/3 x squared, anything times 0 is just going to end up being 0. So like what we said before, we know in this case, if we have our basic form, 1/3 x squared, we're just going to be starting with our vertex at the origin. So let's say if I wanted to plug in another point, I could plug in 1 into that function, and if I do 1/3 times 1 squared, again with 1 being used as an x value, I would end up getting 1/3 as a y value. We could plot that, but we could plot a point that's a little bit easier. 2 I don't think is going to work great either, because 2 squared is 4. 4/3, again, we could put it onto the graph if we wanted to, But I'm just going to go to our next point. If I plugged in 3, 3 squared is going to make a 9, and then 1/3 of 9 is also going to be 3. So what I'm really doing to fill out this table is I'm taking each x, plugging it into the equation, and then just seeing what I'm left with in terms of an answer for a y value. And your calculator could help if you're having trouble plugging those in. But I'm just going to go to that last point that we made. So if I plugged in 3, and 3 was the y value as an answer, that means that this is going to be a point on my graph, the coordinate 3, 3. So if this is the coordinate that we found from our table, and we also know the vertex from our table is 0, 0, that's 2 points to help make our U-shape. All I got to do to finish the U-shape, because it looks like so far I could make part of my parabola, I could find the other part again by using reflection. So since I started off, it looks like 1, 2, 3 points to the right of my axis of symmetry. I could go the same distance on the other side. So if I was 3 units to the right, I could reverse that and go 1, 2, 3 units to the left. And that, it looks like, is going to be another point that would end up being on my parabola. So again, using symmetry, now I have a point on the other side, would be at -3, and still with a y value of 3. And to finish that parabola, I could just make that U-shape going through that second point. If we also want to identify domain and range, this is a little bit of a review from earlier. Domain, we always want to think in terms of our x values, range in terms of our y values. So for pretty much all of our parabolas, our domain is going to end up being what we call all real numbers. If you remember that from earlier, we could abbreviate that as just ARN. So a lot of times you just say darn because that's domain is all real numbers. And that means that we could go all the way to the right, we could go all the way to the left. Any positives, any negatives work for x, so does 0. So if I could plug in any x and it works, that's all real numbers. What we do have a limit though is how high or low this graph is going to go. Because we have a minimum point with our vertex, can't go any lower than that for our y values. We could say that y can be greater than 0. It can also be equal to 0, but we can't use any negatives, so that's going to be our restriction. Y has to be at least 0. With the second graph, just pointing out what we had, again, we had symmetry again. What I did was I changed the actual equation to make that a little bit easier to fit onto your graph. But I did the same thing, plug in a few x's, see what I'm left with for my answer for y. And then if I have points on one side of the graph, I can use symmetry to reflect over and find the other side. So since we've looked at direction already in terms of do I have a positive graph that's opening upwards, or do I have a negative graph that's opening downwards? We already know that we know the direction based on the equation, but we could also look at this and judge quickly about the widths or how wide or how narrow these are. So if we notice that last one, 1/3 x squared, that U-shape opened up a bit wider than using something like -2x squared. So the rule there is basically smallest absolute value is going to be your widest graph. So the actual number, for example, -4, is less than 1/4, but 1/4 is a fraction. That absolute value is going to be smaller than -4. So if we're trying to make the widest graph possible, kind of like in our last example, that 1/3 end up being wider than -2 in terms of my coefficient, since that's a smaller absolute value, that made it a wider graph. So our widest graph of these three looks like 1/4 x squared. And then the next widest, because we got to go widest to narrowest, it looks like it's just going to be x squared by itself. So f of x equals x squared is our next widest graph. And then our narrowest graph, again with our largest absolute value, that was -4x squared. So the negative again just means that it would be opening downwards. Since it's got a bigger absolute value, it would still be our narrowest graph. Copying the same thing with our other example. Again, in terms of absolute value, 1/3 is the smallest, so that's the widest. Then 1, absolute value is going to be in the middle. And then 3, opening upwards because it's positive, doesn't matter. We just know that the 3 is greater than our other coefficients, so it's going to open narrowest. If I add or subtract to my equation, I can also tell if that function is going to be moving up or down. This one's a little bit more straightforward. If it's asking a question like how are these graphs are related, I could say something like y equals 2x squared plus 3. Just adding that 3 means I'm going to be taking this graph, it's going to be shifting y equals 2x squared 3 units, and if I'm adding, it's going to be shifting that 3 units up. So relatively straightforward. Again, if I add 3, it's going to be taking this graph, moving it 3 up. If I use that next example, if I use the graph x squared minus 3, it's going to be taking that parent function and shifting it 3 units down. So I can move a graph up or down just by adding or subtracting. And again, kind of like that starting situation, I could use it as this kind of example as a word problem. So height given by a function of time, starting from a certain height, meaning that height is measured in feet, time measured in seconds, and how high I start with. So in that first example, we started from a balcony at 64. Next example, only thing we're really changing is that we start with a tree branch that's 70 feet above the ground. So if I start with this function, again, this is basically telling me how fast an object is falling. I'm going to need to figure out, first of all, how to graph that function, negative 16t squared plus 70, and then use that graph to estimate when our acorn is going to hit the ground if it falls from 70-foot branch. So what I did already was I made this into a table, kind of like with our last example. And in this case, we don't have x's or y's, but what I do have is height and time. And kind of like where x would go in my function, time is going in there instead. So what I did is I just basically crossed out x. We're going to be using time for our variable instead. And similar with our y's, instead of y's, we're just using h for height. And for our graph, we know that we're starting at a height of 70, so I made room for that in my scale. Don't think we're going to be needing too many different times, so I went pretty far to the right with 1 second and then just 2 seconds. And if we're trying to find out some values to enter for my graph, again, all I got to do is plug in some times and see what I'm left with in terms of a height. So what I did was I started from 0, plug that into my equation. If I get my answer of just 70, that means that when I start my graph, 0, 70 is going to be my starting point. So I would start my graph right at that point on the y-axis. If I was going for another point, again, let's say if I just went to the next second, plug in 1 into that same function. When I simplify it, and again, you could use a calculator if you're getting stuck, I would end up getting 54 as a result. So if that acorn falls for 1 second, I'm left with 54 as a height, meaning that I could plot that on my graph. I think that would go about right here. So I'm at 1 second and I'm at 54 for height. And if I take 2 seconds, again, just plugging this into my same function, again, calculator would also work, I'm left with 6 for height. So if I'm at 2 seconds and my height is 6, what we know is that we could basically model this using our parabola shape. It's not falling linearly, but it is kind of taking this sloping downwards path. And if I was making this into a full parabola, what I would be doing is I would be reflecting those points over, except we can't do it here because we have our limits from the actual word problem. I'm starting from this branch and it's falling. I can't go backwards in terms of time. So if we're actually using the graph to estimate at what time does the acorn hit the ground, all I'm going to answer here is we can answer something like just after 2 seconds. Because from my graph, I saw that at 2 seconds, we were at a height of 6. When I was just a little bit after that, we're at a height of 0. Again, a height of 0 is representing that acorn actually hitting the ground. So we're kind of modeling the path of that acorn. Starts from a height of 70 for our branch. It's falling at 1 second, it's at 54 feet. But over the next second, it falls faster and faster. I'm at 6 feet after 2 seconds. And a little bit after that, I've hit the ground because I'm at a height of 0. So if we're also answered domain and range, again, now we're just using t for x instead. We can't use negative time, so I just said that time has to be at least 0. And in terms of our range, we actually have a couple limits. For our height, our highest height was 70. That's where we started on the branch. And the lowest height, of course, when it hits the ground, because I can't go underground with that acorn, I can't go negatives. So for our range, we're using the lowest is 0, the highest is 70, and our height's going to fall somewhere in between the two.